Okay, good morning, everyone. So we start the sixth course today. Uh, the name of the course is Statistical Inference. Well, I've made a spelling mistake here. uh, so what is statistical inference? Let's first understand that. Uh, let's say I want to uh, measure uh, the average height of uh, Indians. All right. Now, how do I go about doing this? One way is that I have the data for every single Indian and I just take it and average it out, and I actually get the average height of all the Indians today, right? On the other hand, this is like almost practically impossible, right? How can you even get the data for such a huge population, let's say? So what do? I say, okay, let me pull out some sample data which is representative of the population. Okay, take the average of the heights of this sample data, and then I say, okay, this sample data's average height is representative of the population height. But now, the moment I have said that this is sample data or statistical data, right? It inherently is going to have some noise. When I say noise, means it is not the accurate one, right? There's some uncertainty involved. So you're saying, okay, with what level of confidence, what is your surety that okay, this is the correct answer, right? So you have to even account for how much is the uncertainty in your answer. Hmm? So that is what is statistical inference, where you say, okay, I draw some conclusion about the whole population using sample data, using statistical data, which inherently will be noisy. Okay, but I will still have to take care of the uncertainty, right? Or in other words, I can say, so you formulate conclusions from the data and you uh, quantify the uncertainty arising from it. All right, that is important. Now, because the data is not complete, right? So why is there uncertainty? One is because the data is incomplete. Secondly, it could be bad data. Okay, so two reasons why it can be noisy, right? Incompleteness of data or data being bad. Okay, so when say concrete data is available, statistical inference is not required, right? So say assuming we had the heights of each of the Indians, all right, available, we don't need to do any statistical inference there. We actually get the output, right? So what we will do is we're going to use swirl to get a better understanding of the different concepts. Okay, so let me execute that. Uh, so they have a very nice swirl assignment associated with the concept understanding for uh, statistical inference course. All right. In fact, I would recommend all of you also to do the same thing. If you have already enrolled for this course, please go to the class. Wait. All of you, please go into the class, because if you're running the swirl on your machine as well, it'll be more. So there's no credits for the swirl assignment, uh, but nonetheless, it is very beneficial in understanding because it's drawing different graphs, charts, etc. So I'm saying, are you also doing the same thing along with me? Okay, right? So you need to load the library and then you install from swirl and then you start off with swirl. Okay. Okay. So are you in sync? All of you are here now? Are you at swirl? Okay. All right. So you can read the first example, which is which of the following is not an example of statistical inference? Read through the four options. All right. This is constructing a medical image. In your case, it might be ordered in a slightly different manner. Just but look at the four options that are there. Right? Constructing a medical image, testing the efficacy of a new drug, polling before an election to predict its outcome, recording the results of a statistics exams. So, which according to you is not an example of statistical inference? Recording the results of a statistical exam. Okay, that's what Lavita says. What about the others? No, don't give me option number three. You'll have to because your option number three might be different. In my okay, Sarvani says it is polling before an election to predict its outcome. All right. So what about uh, Raghav, Nandani, Kaustubh, Pratik? Hmm. If you can't figure this out, doesn't matter. Some answer you can give me. You may say I think option number one or two or multiple options also you can tell me. Okay, maybe I'll need to talk about it now. Okay. Uh, uh, just to understand, why is it that the others did not answer? Is it that you're not clear by looking at the examples or uh, any other reason? Like I see only Sarvani and Lavita having answered it for me. No one else answered it. Any specific reason? Uh, or you're not sure? Looking at the example, you can't make out. Are you still busy opening Swell for yourself? Testing the efficacy of a new drug, all right. Okay. Rohan has given me some answer. Pratik says constructing a medical image, all right. Kostub and I guess Raghav are left. With the Swell assignments, it has become really interesting. We look at a concept and then there's an example to see if it is we have understood it or not. Okay, now look at it. What did we say? We say that first of all, the data that is involved in statistical inference is not complete data, right? So it is complete incomplete. That is a inherent thing about it. Okay, then it may or may not be bad. It's not that it's necessarily bad. Okay, so incompleteness of data is the key thing because of which we require statistical inference. And we also said that when the data is concrete, huh? That is all the data is available, then we don't need to bother about statistical inference. Now let us look at out of these four options, which one will not, which one will have complete data with us, right? Which one will have the complete data? Let us look at the medical image, right? So when you're creating the medical image, all right, from the MRI data, will that MRI data be totally detailed? So you're trying to create an image of an inner organ, let's say, right? Do you think? Right. So Lavita says recording the results of a statistics exam will have complete results. So Rohan says exams will have complete data. Right. Right. So just by looking at it, you can make out the complete data will be only in the case of the exam, right? Because every student is giving the exam, and I'm recording those results, right? Though it looks like statistics exam and that can be confusing, but in reality that is the only one which is complete data. But let's look at each of these individually first. Okay, how can we ensure that the others? So now MRI data will not be complete, right? It just captures some data and then from that you're constructing the image, right? Now testing the efficacy of a new drug. Efficacy means how effective it is, right? So you're not giving it to every single patient, you're just giving it to some patients. And from the outcome that you get, you're saying, okay, you're concluding that this drug will be good for the rest of the population, right? Same, third one is polling before an election to predict its outcome. It did not said polling before an election. So basically what here polling means is exit polling, right? If suppose it was polling before an election, okay, to decide the outcome, then it would have been not statistical inference, it would have been the actual concrete data. Are you getting this? So there is always a difference between exit polls, right, and the actual polling. Just imagine how to give you a glimpse of what is the difference between actually, getting the result and predicting it. Let's say we were to choose our prime minister based on prediction, right? Just choose sample data and whatever they say, we decide who is going to be the country's prime minister. Hmm? On the other hand, we actually have to do polling. Why do we have to actually do the polling? Because this uncertainty is so high. We can't afford that uncertainty, right? But at the same time, still, like for example, in the US, the elections happened, and based on the data, it was able to the prediction was correct. Even in India, right? The exit polling was able to predict how many seats BJP will take, how many seats Congress will take. So, and that this kind of exit polls are done on a very small sample because it's very, very expensive to do it on a huge sample. You got it? Have you understood this concept clearly now? Hmm? With the help of this example, let's move ahead. Hmm? So I give 4 as the option. So now it says, so when we say, so So all the numbers that you compute from a sample data, each of these is called a statistic. When you say statistics, right? So statistic, say for example, mean is a statistic, median is a statistic, another statistic. So like that, each of these are statistic, right? Singular, right? So we have statistics that are computed from the sample data, and let's also look. So we're just looking at certain concepts. What's a random variable? So an outcome from an experiment, okay? Let's say the simple case of an experiment is rolling a die, right? So if I roll a die, what can be my outcome? The outcome would be any of the values 1 to 6, right? And what will be the superset of the outcomes? It is 1, 2, 3, 4, 5, 6, right? So any of the one values is a random variable, right? And the total overall set, I can call it a random variable, right? So I need not say one is a random variable or two is a random variable. I say my random variable is values from 1 to 6 with some finite probability, all right? So that whole thing will be the random variable. You understand the difference? Normally a variable will have just one value. The word random makes it such that now you're saying, okay, you have multiple values, but each of these values have a probability. We will look at this in more detail as we go ahead. Now, what are we doing? We're saying that we have these random variables that we are generating, right? Say, for example, throwing the dice. And then we apply formulae or certain concepts on these random variables. that will give rise to additional random variables. Okay, say, what do you mean by deterministic processes? These processes actually do not have any randomness involved. Okay, so for example, if I want to calculate the mean of a random variable, that mean, the methodology or the whole process will be still the same. I'm saying a plus b plus c divided by 3, right? That will give me the mean. So there is no randomness involved in the process involved. So I capture the random variables and I apply some mathematics to it. Let me call it some mathematics. It will give rise to another set of random variables, because one set of random variables or a random variable can only generate another random variable, right? So these additional random variables, if you were to distribute them, right? Say random variables were to be spread given a distribution curve. Let's say if I was to give the random variable uh, of throwing a die a distribution, right? How will that look like? That'll be something like this. Let's say I call it my value, all right? Value for the random variable. Okay, so it can be, so here it is 0, all right? So it can be 1, 2, 3, 4, 5, 6, and let me call this probability, all right? So my probability will be 1 by 6 in each of these cases. So this is my distribution for the random variable. On the other hand, if I was to take the average of this, right? So if I was to take the average of this, I get 1 by 6, right? So I get mean of x is 1 by 6, all right? So, so I suddenly have a new distribution. You got this concept? Hmm? All right. Hmm? So let's move ahead. Okay, now inference. So when we say statistical inference is divided into two parts. Again, these are just words that we're talking about right now. We will look at, as we move ahead, we will see what all these means. But right now, giving, I'm just throwing out some words. So we say one is called frequentist statistics and another is Bayesian inference. All right. In frequency statistics, there are two parts. One is hypothesis testing. This is what typically you've learned also, right? And second is confidence intervals. All right. And then there's a Bayesian inference. So all of these terms, if you need to understand, we need to understand probability first. Okay. And that's why we say, okay, first we'll jump to probability. Okay. So we move to, so what is probability? So we say in the outcomes of an experiment are there, and all the outcomes, right? So for example, die roll, right? So we have all the possible outcomes. There are 6 outcomes, 1, 2, 3, 4, 5, 6. The probability of a particular outcome, in out of all of these possible outcomes, the probability of a particular outcome, how do you measure that? You say is equal to the number of ways the outcome can occur divided by the number of ways for all the possible outcomes. For example, rolling 5, you can get it one way, right? Out of 6 ways. Is this clear? Hmm? Looking at a little more complicated example for to satisfy this. Let's say if I was to roll 2 dice, right? I say, what is the probability of getting the sum as 3? All right. So the probability of getting the sum as 3. Uh, uh, what will be my answer? I roll 2 dice. What is the probability of getting the sum as 3? Uh, the probability, I am rolling 2 dice now. First, what are the number of ways for all possible outcomes? First, how many possible outcomes are there if I roll 2 dice? Possible outcomes are 36, right? Is this clear? Huh? Okay, now don't confuse possible outcomes with possible outputs. How many possible outputs will be there? Assuming that I'm interested in the sum. If I'm interested in the sum of the roll of 2 dice, how many possible outputs will be there? No. There will be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12. So 11, right? So you have 11 possible outputs. Like when I roll the die once, one die I'm rolling, there are 6 outcomes and 6 outputs. But when I'm rolling the die, so basically let's go back to our previous example. That makes it clear. What did we say the theory is? We say deterministic processes applied on random variables produce additional random variables. Okay, so if I'm saying the sum of the uh, outcome on die 1 plus the sum of the outcome on die 2, hmm, so that is going to give me another random variable. You understood this concept now? See, if I'm rolling two dice, the outcomes are 36. From those 36, I can say if I was interested in the sum, right? Then I have how many different outputs? Huh? This concept should be clear to you. How is the outcomes different from additional outputs that you're creating? My outcomes will be fixed, and outcomes need not be numeric. Say, let us say my dice are specially created so that instead of numbers, they have colors on them. 6 different colors on the die. Do you see this? So if I have 6 different colors on the die, the outcome is in the terms of colors. I say red, comma blue, green, comma orange. It is not numbers, right? So so my outcome need not be in terms of numbers. My outcome will be in terms of what has actually happened in that experiment. What I'm capturing. All right. My data, sample data. So that is my sample data. Out of that, then I'm creating random variables. Okay. Is this part clear to you guys? Okay. So coming back to our question here, I'm saying so we're rolling two dice, right? So the number of possible outcomes are 36. Okay. So number of ways 3 can occur. How many number of ways 3 can occur out of 36 possible outcomes? Two ways, right? 1 and 2 and 2 and 1, right? Combination of 1 and 2 or 2 and 1 gives me 3, right? Which means the probability will be 2 by 36, correct? Or 1 by 18. Clear? Huh? So, though it's a simple example, why I'm giving it in elaborate terms is so that you understand the concept behind it. All right? So, this is how you calculate the probability of a particular outcome. Okay? Or a particular, so not necessarily an outcome. Here, what we are doing is outcome can be interchangeably used as output or what I am interested in, or a random variable you can say. Okay? So, now let's call it an event rather, right? So, outcome is one thing. So, an event is the occurrence of something, right? So probability of an event or an occurrence E is always, now another thing, it will always be between 0 and 1. Only then it will be a random variable, right? Because if the probability is 0, then means it is an impossible event. It is not, it cannot happen. On the other hand, if the probability is 1, that means it's a certain variable. It's not a random variable anymore, right? It's not a random event. So there is no concept of probability. So it has to be between 0 and 1 strictly. Is this clear? So strictly between 0 and 1, okay, is the probability of an event happening. Okay. Okay. Now let us uh, Debashri, you may also want to join in the um, Adobe Connect. Okay. So now I'm saying the probability of event A and B both happening. It need not be, but it can be probability of A into probability of B, where A and B are two independent occurrences, each happening in two independent identical experiments. Example, rolling the dice twice, right? So if they are independent of each other, all right, then I say, okay, if my experiment is rolling the die. Okay, Debishri. So my experiment is rolling the die. So I'm repeating the experiment. Okay. So first time I roll it, I get some value. Second time I roll it, I get some other value. Okay. Let's say what is the probability? Say I have a red die and a blue die, right? So what is the probability that I'll get a 4 in both the cases? Hmm? So what is the probability that I'll get a 4 in both the cases on both the die? So first of all, the rolling of one die is not dependent on the rolling of the other die. We know this. So they are totally independent occurrences, right? So now if they're independent, the probability of one is 1 by 6 into the probability of the other, that is 1 by 6. So you get 1 by 36, right? So another concept that you need to understand. So we're just looking at all the different concepts and then building it up, okay? Say, so let's look at this, right? Say if we were to, as we saw, right? So 36 outcomes are there. So these outcomes in this graph are shown to us. At the same time, S is my output here. So I have 11 outputs, and each of these outputs, this is my random variable. S is my random variable. Each of these outputs has a probability. Is this clear? So my probability is shown here: 1 by 36, 1 by 18, 1 by 12, 1 by 9, 5 by 36, 1 by 6. Okay. So now, as we now another thing is that probability of A and B happening both, two events, right? So let's say event A, event B, both of them happening is given by the Venn diagram concept. We know this, right? Say Venn diagram, let us look at how it works. Let's say single die roll, right? So what are the different possible outcomes? 1, 2, 3, 4, 5, 6. Let me define A as first three numbers, that is 1, 2, and 3, and B as even numbers. In that case, so this is my A event, 1, 3, and 2. My B event will be 2, 4, and 6. So 2 is common here, right? And 5 is out of these two events. It is neither A nor B. This is the superset, we may say whatever is left, right? So what I'm saying is A union B. What is that? Probability of A, right? So probability of A union B. First of all, what is the probability of A union B in this case? What's the probability of A union B if you were to just directly look at it? Probability of A union B, how much will that be? Know that whenever we talk about probability, it has to be less than 1, right? Or typically less than equal to 1, between 0 and 1. Yeah. So your probability will be 6 outcomes overall, right? A union B cover 5 outcomes, which means 5 divided by 6, right? So probability of A union B will be 5 by 6, okay? And this is equal to probability of A. Probability of A is 3 by 6, right? Plus probability of B is another 3 by 6, all right? And what is the probability of A intersection B? So there is only one value, 2, okay? That is one outcome, that is minus 1 by 6. Is this clear now? How we got it, right? So, so this is how you can get your probabilities, okay? Moving ahead. So now understand that a random variable is a numerical outcome of an experiment. So say, let's say I'm tossing a coin. The coin will only give me a heads or a tails. So my outcomes actually are heads or a tail. So how do random variable get into the picture now? Tell me. I'm saying I'm tossing a coin. The coin toss can only give me a heads or a tails. Where does the numerical outcome come into the picture? What do I do to make it numerical? You understood my question? No. See, I'm saying I'm tossing a coin. Okay. So I can only get a heads or a tails. So where is the random variable coming into picture? Because I'm saying I'm defining that my random variable is a numerical outcome of an experiment. My experiment was tossing the coin. Okay. How do I fix it up? Outcome is discrete. That is true. So, all right. So it can be treated as binary, Rohan says. All right. In that case, it gets taken care, right? I can say, okay, my heads is equal to 1, my tails is equal to 10, right? Or my heads is equal to 0 and my tails is equal to 1, or my heads is equal to 1, tails is equal to minus 1, whichever way. So I basically assign my outcomes to a numerical number, and that becomes then the random variable. But understand this, that I am assigning it. So I could have assigned 0 and 1, or I could have assigned uh, 1 and 0, I could have assigned 1 and 10, or anything. That's my assignment. Is this clear? Right? So now the next thing that I'm saying is, so my random variables are of two types. One is discrete and another is continuous. What do you mean by discrete? See, there is a countable number of possibilities that are there in the discrete random variables. Like say when I'm tossing a coin, there are only two possibilities. When I'm throwing a die, there are six possibilities, right? When I'm throwing two dice, there are 36 possibilities. Okay. On the other hand, continuous, what will happen is it is any value on the real line or a subset of the real line, right? So basically, it's a real number. Hmm? Okay. So if it's a real number, uh, uh, what is it? Uh, if suppose I say that I measure the height of, so I want to measure somebody's height, all right? Will it be treated as a discrete random variable or continuous random variable, or rather discrete value or continuous value? Measuring somebody's height. It will be continuous. Lavita says it will be continuous. Rohan says it is continuous. Kaustav says discrete. Now your scale can have only some measures. It will say millimeters, or let's say you use vernier caliper to measure somebody's height. Okay, so it can go up to tenth of a millimeter, right? So what is happening? You are limited by your measurement equipment, but actual value is still continuous, right? You can't get the actual output, but it is still actually continuous. So you understand this very fine difference, that it will actually be continuous, though it will be reported as discrete values. Say tomorrow you start getting such scales which can measure up to 1/10 of a millimeter. Say today whatever scales we are using to measure the height measure up to a millimeter, right? Tomorrow we start getting such scales, some digital kind of scales, right, which you place on the head. They will still measure, but they will measure up to some decimal places, which means their precision has increased. So precision is not the same as continuity or discreteness. Understand that. Is this clear? Huh? Discreteness means there is finite outcomes only. There is a jump in the value, right? So all your continuous, typically when is your variable continuous? When it is values of time or distance or maybe some biological process. So typically it will be all continuous. Okay. And so okay, let's look at some of the things from the swirl assignment now. Okay. So now give me an example, which move ahead with the second part. Uh, which of the following could not be a source of bad data? All right, so second part of the SWOT assignment. So it's good that I've taught you some concepts ahead. I'm coming back to the previous concepts. Okay, so it says which of this is not a source of bad data? Poorly designed study, selection bias, small sample size, randomly selected sample of population. So Lavita says her option is randomly selected sample size. Okay. Nandana says small sample size. Pratik says selection bias. Okay. Raghav says small sample size. Okay, so Lavita says randomly selected. Yeah, Lavita said that. I already read that out. Saravani says randomly selected. Okay. So Pratik is saying selection bias. Okay. Okay. So let's look at it. Look at poorly designed study. I guess you are all in sync. You're saying okay. Uh, that poorly designed study is a source of bad data, right? Right. So second is selection bias. we are clear that selection, if there is a selection bias, there it will be bad data, right? So either data can be bad or incomplete or both, right? So now if there is selection bias, clearly there is bad data. Then we're saying small sample size. If the sample size is small, right, chances are that it becomes bad data because it can inherently become biased, right? Say for example, if I want to predict elections like Rohan pointed out, acha, you guys, if you do your chat in Adobe, what will happen is others can also read what you're writing, so others can also get involved. Okay, so you may just need to, I don't know if it is convenient for you or not. So using the chat of Adobe will help others also to uh, that's okay. Pratik, options will be different. But they will be still same choices, right? They'll be ordered in a different manner. That's fine. Okay, right. So let us look at the small sample size. Now, small sample size is a tricky one, right? We're saying, okay, sample sizes are supposed to be small. That is why they are samples. But if it becomes too small, right, then also there are chances of bad data happening. So this is another important thing. Okay, and then fourthly we are saying randomly selected sample of population. Now the moment it says randomly selected, the chance of bad is less, right? And then it says sample, it does not say small sample, then also chances are less. So we say, okay, the first three, so fourth is the possibility that it is not a, in my case, okay, so is that it is not a example of bad data. Okay, so the next one is, so with statistical inference, we use data to draw general conclusions about population, right? Which of the following would a scientist using statistical inference techniques consider as a problem? So let's look at, so which is a problem for a scientist here? So data sample is representative of the population. One, study has no bias and is well designed. Three, contaminated data. This one is obvious actually, right? Contaminated data. No, no, there's fourth option also. Counting sheep. Okay. Oh no, no, that's another one now. All right. So it says, which of the following is not an example of SI in action? It says determining a causative mechanism underlying a disease, testing the effectiveness of a medical treatment, estimating the proportion of people who will vote for a candidate, counting sheep. Okay. So this one is obvious, right? Again, but if you, I mean, but if you were to actually, Rohan's question is, should we consider from where to pick so that the randomness is high? Yes, Rohan. Say geographically, say for example, let's say we want to predict the results of Chandigarh. All right. Now, what I would want to do is, so I have say 50 sectors in Chandigarh. So I want to pick up 10 samples maybe from each sector, right? Either each sector, or I say, so if I don't want to take 10 samples from each sector, all right, so in this case my sample size becomes say 50 into 10, 500, sorry, right? So I say I want to take my sample size only as 200, and I still want to pick up 10 from one sector. Why so? Because practically it will be so difficult to go to all the sectors. So I say, okay, I randomly first choose 10 sectors. All right. So there is a randomness in the selection of the sectors. Once I've chosen some 10 sectors, out of each of those sectors, I select 10 people randomly. That makes it easier, right? So, so that is, so basically how you select makes everything, all the difference. How do you sample your data makes the big difference in whether it is going to be bad data or is it going to be good quality data. Is it going to be really truly random or representative of the population? Basically the data should be representative of your population. That is the key thing here. So, but I'll not jump to counting sheep as an answer. Let us knock off that answer and let's look at each of the other ones, right? Determining a causative mechanism underlying a disease. So I'm saying I'm determining the causative mechanism. Why should it uh, uh, be an example of statistical inference? Say some disease is there, right? When I'm saying mechanism, mechanism is deterministic. I'm trying to find out the cause of it. So why should that be statistical inference? Are you getting my question? Why should the determining a causative mechanism underlying a disease should be a example of statistical inference? Right. So we're capturing it from the symptoms of disease, or how we're capturing is it? Data is incomplete. Right. The main thing is, so we will never have all the causes, right? So our data is incomplete, plus we will have limited number of patients who have that disease, right? So main thing is that we have limited incomplete data. Not everyone has the disease. Only those who have the disease, from there only we can deduct, right? Similarly, testing the effectiveness of a medical treatment, only because some patients we will test the medicine on, right? You don't keep testing it on every single human being, right? Similarly, so all the rest are anyways obvious, okay, right? So we want to emphasize, we have already looked at singular, right? And so there are two. So we've done this, okay? Let us move to the probability slides, okay? So this we already know, right? We've already done this, okay? Mm. Okay, so what's the probability of rolling an even number uh, when I just roll one single die? It's a very simple question. I'm just asking it for 1 by 2, right? Okay. Okay, we have already gone through this. Okay, another important thing is the sum of the probabilities of all the outcomes has to add up to 1. Okay, so if all the outcomes are equally likely, then each of the probability of each of them will be 1 by n. Okay, like for example, rolling one die, we have the probability as 1 by 6 for each of them. Whereas when you roll two die, then the probabilities change. If you saw the previous slide here, right? So then the probability is not constant. The probability of getting 2 is 1 by 36, probability of getting 3 is 1 by 18, and so on, right? And we have seen this also in, suppose you roll the fair die twice in succession, what's the probability of rolling two fours? We already know this, right? Suppose you roll the fair die twice, what's the probability of rolling the same number two times in a row? So what's that? Probability of rolling same number two times in a row. 1 by 6, right? Consider the experiment of rolling two die, one red and one green. Assume that the die are fair and not loaded, so they are fair die. How many distinct outcomes are possible? How many distinct outcomes are possible when you roll two die? I've already answered that for you previously, but just to check. 11, all right. Sarvani said 11. Uh, Lavita says 6 outcomes. Yeah, for this particular case, read it again. Read the question again. 36 Rohan says 6 का option ही नहीं है. Raghav says all right, doesn't matter. Let's assume 6 का option भी हो, यहाँ गलत है. This is the question, how many outcomes? 11 Nandana. Maybe if you use the Adobe chat, it'll be better, no? Others can read your outputs. Pratik also says 11. Come back. Let's come back to our definition. Let's come back to our definition. Okay, so Lavita, what's your answer? 36. Okay. What did we say? Outcomes are all possible outcomes. What happened? Not necessarily what we created out of it. What is 11? 11 is the sum of those outcomes, right? I'm saying the sum of the numbers shown by the outcomes is gives me 11. Are you getting this? You see the difference? So you understand the difference between 36? Yeah, it's an output which I have termed as output, right? Outcomes are 36. Out of those 36 outcomes, I can create any number of random variables. Are you getting this? Like coin toss, we created one random variable with possible values of 0 and 1, right? With two coin tosses, I could have created uh, a different kind of random variables. So this concept you should be very clear with the outcome part and the output part. So don't confuse that. The answer here will be 36. Okay. If an event E can occur in more than one way and these ways are disjoint, then probability of E is equal to the sum. We have already seen this, right? So rolling two dice, what is the probability of rolling 10? So if you're rolling two dice, what is the probability of rolling a 10? Right. So Rohan, for example, says outcome is an happening, output is an effort. Right. So outcome is something that has just happened, right? Output is what you will derive out of that outcome. So here 3 by 36, right? Because 10 can come as 5, 5, 5, 4, 6, 6, 4, right? So three outcomes out of 36. What sum is the most likely when rolling these two dice? When two dice are rolled, what is the sum that is most likely? 70 says 12. 70, are you logged in into Adobe also? Is it inconvenient, slightly inconvenient to whose combinations are highest? Yeah, right? Lavita, you say 12. Sarvani says 12. Okay. Rohan says 12. Okay. Okay. Can you please, three guys gave me the answer as 12. Can you please explain how 12? It might be correct or it might be wrong. I just want to understand your logic. All of you can write down your logic and maybe in Adobe. Each of you can read each other's logic. The probability of 12 occurring is more. Okay. No, no, it's 9. Okay. Think of it again. How would you get 9? How would you get 12? Just give me 1 second. Now. So tell me 5, 4, 4, 5, 6, 3, 3, 6. Whereas 12 is only 6 and 6. Right. Huh? So, so which has more probability? What about 7? How many possibilities are there for 7? How many possibilities are there for 7? Tell me. 7 will be the highest, right? 1, 6, 2, 5, 3, 4, and then the reverse of that. No? So, I mean, and how do you come to it immediately? Say if the numbers are between 2 and 12, 7 lies somewhere in between, and typically something that in between will have the highest probability. Okay? Okay, give me 1 second. I'm recording the lecture as well. My hard disk is getting full. I just need to shift some of the data. Okay, I'm just stopping the recording. Okay, and so we can continue again.